actually took him 6 weeks of calculation for just a 24-hour forecast. And he didn't actually just imagine it, he tried it. He took real atmospheric pressure data from May 20th, 1910. He applied the equations to a section of Central Europe and he spent months working through that maths. And what was the result? He predicted the atmospheric pressure would change by 145 hectopascals in 6 hours. But the actual change was just 1 hectopascal. He was off by a factor of 145. Now you see, a lesser man would look at that and give up, right? Richardson looked at it and said, the equations aren't wrong. The input data was bad, and the framework is sound. So, that particular distinction, the bad equations versus bad data, is going to be the thread that we're going to talk about this entire talk. So, hold on to that. Moving on from human calculators to supercomputers. Now, in 1950, we discovered ENIAC, the first electronic computer, which runs the first numerical weather forecast. And it took 24 hours to compute just a 24-hour forecast. So, which is kind of useless, right? But the principle you see in use in that actually worked. In 1960, the first weather satellite goes up, TROS 1. We can now see the Earth from space. First global weather model runs on a supercomputer. And then 2023, Google's GraphCast AI model predicts a 10-day forecast in just 60 seconds. So the same equations that Richardson was working with, just incomprehensibly with more computing power. So as you see, that dream never changed. The tools, or as we say, the modern tools, just finally caught up to that. So I would like to give like a quick math challenge here. Richardson needed 64,000 people to solve that one day forecast, right? Do you know how many equations does a modern weather model solve per forecast? Does anybody want to take any guess? Okay, so it actually so it okay, so it actually is about 10 to the power of 12. 9 million 3D grid cells, 6 variables each, thousands of timestamps. That's what's happening every 6 hours on supercomputers around the world, just so your phone can tell you to bring an umbrella. Let's go to Act 2, which is the fluid. Right. So, what exactly is the atmosphere mathematically speaking? It's a fluid, not metaphorically, literally. It behaves like water. It has mass, density, viscosity. It flows from high pressure to low pressure. It has turbulence. The same equations that describe water flowing through a pipe describe air flowing across a continent. Same underlying physics, wildly different scales. Now, here's an analogy that I love that I would like to share with you. If imagine stirring a jar of honey. Now, imagine that you're stirring air in the same way. Both are governed by Navier-Stokes equations. The honey is just more obviously a fluid because you can see it, right? Air is invisible, but it's doing the same thing, just a lot faster and across thousands of kilometers. The atmosphere also acts like a heat engine. The sun heats the equator more than the poles. That temperature difference drives winds, which redistribute heat. And it has this extra complexity because of phase change. So, as you see, water turns into vapor, back into droplets, and it releases heat and drives more motion. So, it almost feels like it's alive. Now, here's the practical problem. Now, the atmosphere is continuous. Every cubic centimeter of air is slightly different. You can't write one equation for every atom, right? Because there are something like 10 to the power of 44 particles in the whole atmosphere. So imagine writing that many equations. So now, but what do? We cheat a little, but in a beautiful way. So stay with me. We divide the entire atmosphere into a 3D grid of boxes. Each box gets one set of values, which is it can either be temperature, pressure, humidity, wind in all three directions. So we assume that this box is uniform. And then we solve the equations for each box and pass the results to neighboring boxes. Think of it as Minecraft. A lot of people here would have played Minecraft, right? But the actual world is smooth and continuous. But in Minecraft, it is represented as blocks, smaller blocks. So it's more realistic and it's more computational. Modern global models uses blocks roughly around 9 kilometers wide. There are about 9 million of them stacked in 3D. So every 10 minutes, the computer solves the equations for all of them, steps forward in time, and then repeat that same thing again and again. So, actually, quick question for the room right now. We talked about grid boxes. Bigger boxes are cheaper to compute. Smaller boxes are more accurate, but it actually costs a lot. The 1970s model ran 100-kilometer grid boxes. You could see continent scale weatherfront. That's it. Modern high res models run 1 kilometer boxes. You can see individual thunderstorms. So here's the trade off that's worth knowing: half the grid size and you need around 16 times more computation. I repeat, 16 times more, not twice, because you have more cells, and you also need shorter time steps. If you had a forecast that takes 3 hours to run at 1 kilometer resolution, what resolution would you use if you needed the answer in 30 minutes? Does anybody want to take a guess? So it's actually that it's not even operational meteorologists also wrestle with this every single day. Now, so we go to Act 3, which is the data. Now, I would say something very bold, okay? This is genuinely one of the most important slides in this whole presentation. So you need to really be focused on this one. Now, I would quote this: given a perfect mathematical model of the atmosphere, the only thing determining forecast quality is the accuracy of the initial conditions. Now, what does that actually mean? The equations are deterministic. If I give you the exact state of every air molecule right now and perfect equations, you get a perfect forecast. That's mathematically guaranteed. The problem is that exact state of every molecule right now part. Because any error in your starting point, any error at all, will grow, and it will grow exponentially over time. That's not a flaw in our models, that's just a law of mathematics. Good equations plus bad data equals a bad forecast every single time. So, how do we actually measure the atmosphere? 200 weather satellites orbiting right now. They give us temperature profiles, cloud cover, sea surface temperatures, coverage across the entire planet. 900 weather balloons launched every single day from 900 locations around the world. They float up to 35 kilometers, measuring temperature, pressure, humidity, and wind the whole way up. 2,000 Doppler radar networks. These are the ones that track storms in 3D that right now. 700,000 observations a day just from commercial aircraft. Planes automatically report temperature and wind every few minutes while they are flying. 1,200 buoys floating in the ocean. 11,000 surface weather stations on land. So, all of this together generates about 40 million observations per day. 40 million observations. And you know what the cool thing is? It's still not enough. We have about 40 million observations, as I previously told, and we have 9 million grid cells, each needing 6 values every 6 hours. But the observations don't line up with the grid. They are scattered, irregular, and some are more accurate than the others. This is what we call as the data assimilation problem. But the solution to this is actually very elegant and beautiful. You take your previous model forecast, which has physical structure but has accumulated errors over time, and you blend it with your new observations using weighted statistics. So each observation gets a weight based on how accurate it's known to be. The result is the most optimal estimate of the current state of the atmosphere. It's essentially the same mathematics used in GPS navigation, stock market rise models, and self driving cars. So it's basically everywhere around us, as you see. It's in Kalman filters, Bayesian updates. So you see, such a small concept is used in our everyday life that we previously didn't even know of. So you're basically combining with what you knew before and what you just observed, which is weighted by confidence. And out comes the best possible starting point for the next forecast. But unfortunately, we can't measure everything. So here's the uncomfortable truth. Now, 70% of the Earth is ocean, as we previously know. So we have far few sensors there because it's really hard to reach the ocean bed. 99% of the atmosphere remains unmeasured, and grid cells massively outnumber them. And our balloons can only go up to 35 kilometers. And above that, the data that we have is very sparse and very few. And our main global models only run every 6 hours. So we're always forecasting from data that's slightly old. But these gaps aren't engineering failures, they're just fundamental limits. You can't put a sensor in every cubic kilometer of the sky, right? So those gaps are exactly where forecasts go wrong, especially for fast moving storms. The Act 4, the butterfly. Before starting this act, I would like to give a quote by Edward Lawrence, which is: does the flap of a butterfly's wing in Brazil set off a tornado in Texas? Let's learn a little more about this guy, Edward Lawrence. So, he, in 1961, our MIT meteorologist, Edward Lawrence, is running a weather simulation on an early computer. He wants to rerun a section of the simulation to look at it more carefully. But to save time, he doesn't start from the beginning. He starts partway through, typing in the numbers from his printout. So he comes back later, and the simulation has completely diverged from the original. It has the same equations, it had the same starting point, but it was completely different weather. So he thinks the computer is broken, but when he checks it, it's actually fine. But then he figures it out. Just give me a sec. So sorry. Yeah, so as I was saying, he thinks that the computer is broken, but when he checks it, it's actually working fine. But then he figures it out. The computer stored numbers to six decimal places, which was 0.506127, but his printout actually showed 0.506, which was just a difference of 0.000127. That is less than one part in a thousand, but it actually changed everything and the entire forecast collapsed. He published his conclusion in 1963. Atmospheric systems are so sensitive to initial conditions that long range forecasting is not just currently impossible, it's fundamentally, mathematically, and permanently impossible. And that's a big claim, but it actually turned out to be correct. Now, what does chaotic actually mean? Now, I want to clear something up because the word chaos gets misused constantly. Chaos does not actually mean random. This is really important. The Lorentz equations are perfectly deterministic. Same input, same output. Every time, always. No randomness whatsoever. Chaos means that tiny differences over time leads to enormous differences in output. It's not random, it's just very sensitive. And this means that better computers don't solve it. More precision helps in the short run, sure, but the exponential error growth eventually overwhelms any improvement in precision. It's not a computing problem, it's just a mathematical structure. And chaos doesn't mean unpredictable forever. 1 to 3 day forecasts are incredibly accurate. Even 7 day forecasts carry real information. The system becomes unpredictable, but gradually, which is actually useful to know. So here's what makes chaos very mathematically profound. Now, as you can see, these are three Lorentz equations, which makes up the Lorentz system. Rate of convection, which is denoted by X, horizontal temperature difference, which is denoted by Y, vertical temperature distortion, which is denoted by Z. And that's it. And yet the solutions to these equations never repeat. The system orbits around these two wings. You can see the butterfly shape on the right, switching between them unpredictably forever. Change the starting value X by one part in 100,000. And after 10 simulated days, you're on a completely different trajectory. Does anybody find that genuinely unsettling? Because I kind of do. The universe is deterministic in theory. If you knew every starting condition perfectly, you could predict everything forever. But in actual practice, you'd never do know it perfectly, right? And the gap between perfectly and almost perfectly is infinite in consequence. So, as you can see, this 10-day wall. So, what does this actually mean? In days 1 to 3, you see it has 95% accuracy for temperature, wind, and precipitation, which is better than any human forecaster in history. And that's genuinely remarkable. But when you come to day 4 to 6, it's still very useful. Large scale patterns are reliable, but some local details do get fuzzy. In day 7 to 9, the storm tracks can be off by hundreds of kilometers and we won't know. So the details become very unreliable. During day 10, you're barely above what you'd get just by looking at the historical average for that time of the year. And day 14 and beyond is just consult or climate average. The forecast has no real signal left. And here's the thing I really want you to take away from this: that 10-day failure is not a failure of technology. It's not a funding problem. It's not something Moore's law will eventually solve. It is a law of mathematics. It follows directly from the positive Lyapunov exponent, which we will discuss in the later section of this presentation. You could build a supercomputer the size of a solar system, and you still wouldn't be able to push that wall past about 2 weeks. So the information is there, but we cannot extract it. So, if chaos is a mathematical law, how do we deal with it? So, just a little introduction to ensemble forecasting, which will be later covered in detail. But so, instead of fixing this, we actually embrace it. This idea of ensemble forecasting is is works on this way. So you run the weather model not once but 50 times, and each run starts from a slightly different initial condition, all within the range of your observational uncertainty, of course. And you look at what 50 runs produce, and when they all agree, we have the highest confidence. And the in that section, the atmosphere is in a stable predictable state. And when they fan out in different directions, you're in for a chaotic regime. So expect surprises. The European Center for Medium Range Weather Forecast, which is ECMWF, the best forecast center in the world, runs 51 ensemble members for every forecast. That's why a weather app sometimes say 40% chance of rain instead of it will rain. The 40% is real information. It's the fraction of ensemble members that produced rain. Okay, so right now I would like to do a little fun Q&A session for to wrap things up in a beautiful way. So I would like people to participate a little, whatever they want, whatever they think the answers are. So, what mathematician first conceived of numerical weather prediction and when? Does anybody know the answer to this? Okay. So the actual answer, as we discussed previously, was Louis Fry Richardson in 1922. That is, he also ran the first. It was a failure, but it was true. It was the first forecast by hand. Why is the second question goes? Why is it mathematically impossible to forecast weather beyond, let's say, 2 weeks? Does anybody know the answer to this? Okay, so the actual answer is Lorentz chaos theory. The atmosphere is a chaotic system, as we discussed, with positive Lyapunov exponent, and these errors actually grow exponentially over time. This This next question will give you a little taste of the future, and we'll discuss this in length later. But these are the five types of equation that govern all atmospheric motion. These are momentum, Newton's second law, continuity, thermodynamic energy, ideal gas law, and moisture conservation. Lastly, what is data assimilation and why does it actually matter? Can anybody answer this? Does anyone want to try?
I think it's a process of combining real world observations with models, the models we have.
That's actually pretty good. So it is optimal merging of observation with the model that, as you said, the model in background. So here's the big idea in general. So in one sentence, I'll try to wrap this up. Richardson gave us the dream that the sky could be described by numbers. The atmosphere obeys five physical laws, and we decretize them onto a global grid. The initial conditions are everything. We've built an entire planet spanning observation system just to measure that starting point. And Lawrence showed us that the limit, it's not a technological, just a mathematical one, which means that the honest answer to what's the weather in 2 weeks will always be probably something like this, but here's our uncertainty. And that's not a failure, that's a science done right. So my teammate Mannat here would take you deeper into the equation themselves. So here's to you, Manat.
Okay, thank you, Niharika. Yeah, can you just go to the next slide? Okay, so hey guys. So as you have already heard, you understood the history about algorithms and atmosphere, as Niharika told about Lawrence and much more important laws and people. So now let's jump into equations. So now before we understand the relation between the equations and weather forecasting, we have to first understand what the equations mean, how are they defined, and what the terms in the equations mean exactly, right? So now there's a quote which I have mentioned over here that Niharika, could you go to the previous slide? Yeah. So there's a quote that I mentioned here that the atmosphere is not random. It is governed by equations we are still trying to understand. So now you might have heard people saying that atmosphere is random, this and that, a lot of things about it. So they are wrong. They are governed by equations which we are still trying to understand. So now let's jump into the equations that I'll be talking about. So the first topic is first subheading is primitive equations. So the primitive equations are basically the mathematical backbone of all weather forecasting. So the basic idea of primitive equations, or the basic definition, is that it's basically the combination of all the equations that I'll be talking about. So we'll be talking about Navier-Stokes equations. We'll be talking about conservation laws. We'll be talking about hydrostatic balance equations and much more equations we'll be covering in the further slides. So now let's start. So yeah, next slide, please. So now let's start. Let's begin with the most fundamental idea in physics, which is the conservation laws. So these laws are so unique that even nature never violates them. So we'll be talking about conservation of momentum. We'll talk about conservation of mass. We'll be talking about conservation of energy. So now let's begin with the first. So before we begin all this, I have a question. So let's say I'm a student and I have no idea what the laws of conservation, the conservation laws are. I have no idea what conservation of momentum is. So I would like to ask if anybody would willingly want to answer me that in layman terms, explain me what law of conservation of momentum is. So I would like any one of you to raise your hands and just explain. Okay, so it's fine. So I'll just explain what it is. So conservation of momentum basically comes from Newton's second law. So Newton's, as we have learned, what Newton's second law is, it's like basically you're conserving momentum, and a very famous equation is also given, which is force is equal to mass into acceleration, which I have mentioned in the slide. So so let's say that I'm applying this force, let's say in air. So I'm applying some force in air. So as Niharika mentioned before, that so when a force is applying in air, we treat it as some fluid parcel. So now so basically what I mean is that when some force is being applied when some force is being applied in air, so because of that, there'll be some pressure, right? There'll be some pressure gradient, which I mentioned. There'll be some gravity as well. And now when you're applying force, there'll be acceleration. And when acceleration is applied, there'll be change in wind, right? So those all are the main things. There'll be friction. There'll be Coriolis force, which I'll be explaining in the further slides. So that's the basic idea of conservation of momentum, or the Newton's second law, which we apply in air, right? So as in the image I've mentioned, that the mathematical expression of the conservation of momentum. So as there's a word, very important word in this, conservation. So when conservation is mentioned, what we think? We think that the change in momentum will be zero. So what is change in momentum? It's basically the sum of initial momenta minus sum of final momenta, right? So now if change in momentum is zero, RHS becomes zero. So we can write the mathematical expression which I mentioned, that sum of initial momenta, or the total momentum before the interaction, is equal to sum of final momenta, or the total momentum after the interaction, right? So this is the main idea of conservation of momentum. And as we know that momentum is mass into velocity vector, right? And these the below points are something which you have learnt in 11th or 12th, I believe. So the key points, as I've mentioned, that momentum is a product of mass and velocity, as I told before. And if there is no and if no external force acts, the total momentum of the system will not change. As we told, we are conserving momentum. So the there should be no external force, and the objects can exchange momentum, but the total mass remains the same, right? As I mentioned before, the momentum is conserved. And now there are some conditions which you have to follow while using the second law, that uh, as in the key point we have mentioned, no external force acts. So that's one of the most important conditions, that there should be no external force. F the f of so f f ext has to be zero. And the second important condition is that we should use an isolated system. So this is the main idea of conservation of momentum. So it basically predicts wind speed and direction at every grid point in the model. So this thing, don't worry, it'll be explained in the further slides by Aradhya. Yeah. So now let's go into the next conservation law, which is conservation of mass. So now, as again, the word conservation means that there'll be no change in mass. So we can say the further mentioned line, that mass can neither be created nor destroyed. It can only change form. So that's a very important line in conservation of mass. And in this topic, we'll be using the continuity equation, or the law of continuity, which is mentioned in the image. So in this image, so as this is the formula mentioned, which is dou p by dou t plus del into rho v is equal to zero. Now I'll explain the terms individually. So dou p by dou t is basically change in density with respect to time, but at a fixed point, as we can see it's written dou p by dou t, plus del operator, which is also the divergence operator, into rho v. Rho is density of the fluid, and v is the velocity vector, which is equal to zero. Now, the zero basically means that, as I mentioned, it's conservation of mass. So mass is conserved, right? So if mass is conserved, so the net mass change has to be zero. So that is the reason in RHS zero is there. Now, the most important things which we have learned it a lot, that units are the most important thing here. So as we know, rho, which is density of the fluid, density is mass by volume. So the unit will be kg per meter cube. Then t is time, whose unit is second, as we know. And then v is velocity vector, whose unit is meter per second. And divergence operator, which is del, basically it measures the net outflow, right? So now, as in the bottom right, we can see a cylinder, right? So there are two ends of the cylinder. So let's say the left end of the cylinder has some area A1, and some particles are flowing through that area with some velocity V1. And the right end of the cylinder, the area is A2, and the particles that are coming out of that end have velocity V2. So now again we'll be using conservation of mass. So what we know is mass in minus mass out is equal to change in mass inside. Now change in mass is conserved, so change in mass is zero, as we know. So what mass in, we can write it as rho one a1 v1, which is for the left end, and for mass out it's rho two a2 v2 equal to zero, because change of mass is zero, and because mass is conserved. So finally, we can write the equation as rho 1 a1 v1 equal to rho 2 a2 v2. Now, in this equation, there are there are conditions which we should follow. Like, there are conditions for every equation, right? So let's say that in this cylinder, or let's say a cylinder pipe, the density is constant. It's the same. It's the same in both ends. So rho cancels out. So the final equation we get is A1 V1 equal to A2 V2, which we have learned in 11th and 12th, I believe, right? Which is very important equation which we have learned in fluid dynamics, right? Now, why this equation matters? Why does this continuity equation matter? So if we don't, if we don't follow this law, mass could vanish or disappear, right? Sorry, mass could vanish or appear. So it's literally impossible. It's completely wrong. It wouldn't make any sense. The model would just explode. So that is the basic ideology of conservation of mass. That these are the most important points important points and conditions which we should remember while solving the continuity equation, or when we are doing any numerical based on it, right? So now let's go to the last conservation law. Niharika, if you could go to the next slide. Okay. So now this is the third and the last conservation law, which is conservation of energy. Now, again, as in conservation of mass, I told that mass can neither be created nor destroyed, but can change form. Similarly, in conservation of energy, we have to follow the same idea, that energy cannot be created or destroyed, but it can change from one form to another, right? So the now, so in this conservation law, we'll be following the first law of thermodynamics. Now, the equation of first law of thermodynamics, which I've given here, might seem a little complicated, right? But once you simplify it further, it comes to a very basic first law of thermodynamic equation which I've learned in chemistry or physics. So now over here, let me just explain the terms. So dou capital T by dou T again. Capital T is temperature and small t is time. So this term basically means a change in temperature with respect to time at a fixed location or at a fixed point, plus v, which is the velocity vector, the unit is meter per second, into which is into del t. Now where del is again the divergence operator, or you can say the spatial gradient, del of t, and t is temperature as we know, equal to q. Now q is basically the heat source, right? So from where the heat is, coming or whatever. Basically, it represents heating or cooling. So there might be a heat source, or so it basically gives heat waves or cold waves, anything it can give. So example, we can say from the sun, radiation or phase change. So there are much better examples below that. Solar heating, which is basically the sun, which gives us heat waves. There's latent heat. It is released during condensation, and then there's infrared radiation, which basically cools the air. Now there are two important points in conservation of energy, which basically defines this whole idea, or which defines conservation of energy. The first thing is heat transfer, and the second one is balancing energy. Now, balancing energy, as I told, balancing energy basically means that you're conserving energy, right? And conservation of energy, as we know that the change in energy will be zero, so the energy has to be balanced, right? Now, the first point that I mentioned, heat transfer. So now let's say that, I mean, it's not exactly an example. We know it's a fact that sun gives out uh, heat waves on Earth, right? It basically releases UV rays and it hits Earth. But there's a layer on Earth which is called ozone layer. It protects us from the harmful UV rays. Or else, if it wasn't there, we would not be alive. We might get skin cancer. We might die. So what happens is, so the UV rays is coming on the Earth, and then what? So the UV rays are blocked, and then the heat waves are absorbed by the air, and that air spreads the heat waves around, around the surroundings. So it's not exactly uniform, because at some place there might be so it's not uh, spread equally. So now, so this is what basically heat transfer means, that first heat is coming from Earth. So it's basically the heat waves are coming from sun to Earth, and then those heat waves are going from Earth to air. The air absorbs the heat, and then the heat in the heat spreads around. So basically, heat transfer. That heat is transferring. So that is a main idea of conservation of energy, and the equation. So as I mentioned in the slide, the equation tracks. So temperature changes due to local heat advection and latent heat release, which I mentioned in examples of Q or heat sources. And yeah, so that those are the conservation laws. Now let's go to and yeah, Niharika, could you change the slide? So now let's talk about Coriolis effect. So some of you might have heard what Coriolis effect is, or and some of you might not have heard. So it's fine. I'll be explaining it properly. So now these the three laws that I told about. So these using these three laws, we can describe motion, mass, and energy. But in this Coriolis effect, there's one complication with this effect, that the Earth is rotating. So now let's say that Earth stopped rotating for, let's say for 1 minute, or just let's say that Earth never rotated only. So now if Earth never rotated, the air would move in straight lines. But now, since Earth is rotating, there is some kind of deflection that is coming, causing the air to move in some curved motions. So that effect or that deflection is basically Coriolis effect. So now what exactly happens is some opposite force in opposite direction acts in the air, which causes the deflection and causes it to move in curved motions. So now, as I've mentioned the formula that the Coriolis force is equal to minus 2m into omega, where omega doing cross product with v, which is velocity. So okay, so let's look at it individually. So Fc is basically the Coriolis force, or the apparent force acting in the apparent force that deflects the moving air. Okay, and there's one thing over here. There's a negative sign. So the negative sign is basically for the force acting in the opposite direction, which causes the deflection, right? So that is the reason for the negative sign here. M is the mass of the moving air parcel, right? And omega is the Earth's angular velocity. So it's Earth. So this is basically a vector representing Earth's rotation points along the rotational axis. And then we are doing cross product with the velocity vector. So the v is basically the velocity vector of the moving air parcel. Okay. So this is the main equation of Coriolis force. So again, the unit of Coriolis force is newtons. The unit of mass m is kg. The the value of Earth's angular velocity, or omega, is 7.292 into 10 power minus 5 radians per second. And velocity vector, the unit is meter per second, as we know, right? So, and there's one line that I've mentioned. Coriolis is not a real force. If it is Earth's rotation seen from inside a rotating frame, right? So, as I told that opposite force acts and it causes deflection. So now, for a real life example, we have seen cyclones, right? So why do the cyclones rotate? So the reason is Coriolis effect, or the Coriolis force acting. Because of that, because of the Coriolis force, like as I told, if Earth wasn't rotating, the air would move in a straight line. But since Earth is rotating, air moves in a curved motion. So that same idea is applied in cyclones as well, or in storms as well. So basically, this effect causes large scale rotation in storms. So that's the basic idea of Coriolis effect. And as I mentioned, that in northern hemisphere, the winds deflect towards the right hand side, and in southern hemisphere, the winds deflect towards left hand side. And at equator, it's just zero, right? So this is the idea. And then, yeah, Niharika, next slide, please. So now let's talk about a very important equation which we have learned in physical chemistry, which is a very important equation or a very important law, the ideal gas law. So all of us know what ideal gas law is, or what ideal gas equation is, which is PV is equal to nRT. And we know that P is the pressure, and pressure, the formula of pressure is force by area. So we can define it as force exerted by gas particles per unit area, or the unit is Pascal, right? And V is the volume. It's basically the space occupied by the gas. The unit is meter cube or cubic meters. And in the RHS, N is the number of moles. R is the universal gas constant, and the value is it's a constant value. So the constant value is 8.314 joules per mole Kelvin, and we can manipulate it and get it in much other units. And T is the temperature. It's basically the average kinetic energy of gas particles, where the unit is Kelvin. So the average kinetic energy of gas particles, we can use like the velocity formula, that V is equal to root over 3 RT by M, where V is a velocity, T is a temperature, M is a molar mass, right? Now, there's one thing in the definition that I mentioned, that the equation, the ideal gas equation, links pressure, temperature, and density. But in this equation, the ideal gas equation over here, which is mentioned, PV is equal to nRT, there's no density. So now over here, we just have to manipulate the equation. So ultimately, we get the equation as P is equal to rho RT, where P is pressure again, rho is a density, and R is a proportionality constant or the universal gas constant. T is a temperature, right? So now there are some important laws or some important relationships which we should remember or which we should consider. That is, the first one is Boyle's law. So in Boyle's law, temperature and number of moles is constant. So in that case, using the ideal gas equation, we can say that pressure is inversely proportional to volume, right? And then the second law is Charles' law, where pressure and number of moles is constant. In this, we get the relation as volume is directly proportional to temperature. And then comes Gay-Lussac's law, where pressure and volume are constant. In this case, we get two relations, that pressure is directly proportional to temperature and volume is directly proportional to temperature. And the last law is Avogadro's law, in which pressure, volume, and temperature are constant. In this case, we get the relation volume is directly proportional to number of moles. Now, let's look at the units, like some important units. As I mentioned in the bottommost right box, the units check. So over here, as we know, pressure is the unit of pressure is Pascal. The unit of volume is meter cube. The unit of N is moles. The unit of R is joule per mole Kelvin, or you can get it in many other units by manipulating it. Uh, then the unit of temperature is Kelvin. So all these units give energy, whose unit is joules. So why does this equation matter? So basically, it closes a system. So given P and T, we can compute density without any extra equations, as I told, that we can get the equation in terms of density by just manipulating here and there a little bit of like dividing and multiplying mass. We get P is equal to rho RT by using the density formulas, which is density is equal to mass by volume. If we use that, we can just get P is equal to rho RT. So this was the whole idea of ideal gas equation. And this equation links all atmospheric variables together as we have seen. So there's pressure, volume, density, temperature, all of the important atmospheric variables here. So now let's go to the next equation, next important equation. Niharika, could you go to the next slide, please? Yeah, thank you. So now let's look at something new over here, which is so this it's called Lyapunov exponents or the error growth rate. So I'm sorry that the text is overlapping the equation. So I'll just tell what the equation is. So it's basically del of t is equal to epsilon into e power lambda t. So over here, epsilon is the initial error. So I'll be explaining it. And lambda is a Lyapunov exponent, right? And it's basically the Lyapunov exponent or the growth rate. And t is time, as we know. So the unit of the Lyapunov exponent or lambda is basically second inverse or day inverse or year inverse. I'll be telling it in a few minutes. So this is the whole idea. Now I have taken four systems here. So I've taken double pendulum, atmosphere. So these are four different cases. So when we are using double pendulum, or when we are referring atmosphere or global scale, or when we are referring the planets or the solar system, or and we are referring stable system or normal pendulums which you have seen, right? So when we're using Lyapunov exponent, when we are using double pendulum, the Lyapunov exponent is close to 3.0 second inverse. So as we know that the unit of lambda is second inverse or day inverse or year inverse. So there's something called predictability horizon. It's basically telling about how predictable it is. So how predictable the error is or how predictable the growth rate is. That's what it basically means. So the predictability horizon for double pendulum is less than 2 seconds. So now what it basically means, what predictability horizon means, that as the predictability horizon will increase, the more predictable it will become to get the Lyapunov exponent. So for double pendulum, the Lyapunov exponent is high. So now in this case, the predictability horizon is less than 2 seconds. Now let's consider atmosphere, the second system, or global. In this case, the Lyapunov exponent or lambda is close to 0.35 day inverse. Now, if you see this day inverse, it's not second inverse anymore. So in this case, the predictability horizon increases, which is close to 2 weeks. Now let's go to the third one, which is solar system or the planets that we know. Uh, the Lyapunov exponent or lambda is very, very less as compared to double pendulum or atmosphere. It's extremely less, as you can see. It's close to 0.000001 year inverse. And the predictability horizon is much, much greater over here. As you can see, it goes from the predictability horizon increases from close to 2 weeks straight to 100 million years, which is too much, honestly. And let's go to the last system, which is stable system or the normal pendulum. In this case, the Lyapunov exponent is it's so less that it literally goes to negative. It literally goes to the negative scale. So in this case, the predictability horizon increases by large amounts. So it literally becomes infinite. It becomes extremely predictable. Yeah, so this was basically Lyapunov exponent. And the so I'll just tell the basic idea. So it basically means that small errors in initial conditions, as epsilon is the initial error. So small errors in the initial conditions grow over time. So that's what the whole topic or the whole equation or the Lyapunov exponent or the error growth rate means, right? So this is the basic ideology of this. Then let's go to the next equation, which is hydrostatic balance equation. So hydrostatic balance equation now, like basically let's it basically means that we go vertically. I'll explain it in further detail. That okay, so the hydrostatic balance equation, so it basically means, like, let's say, we know that air flows, right? Air flows in atmosphere, or as we know, air flows. So when air is flowing, it'll experience two things. It experiences pressure and gravity. So because of gravity, as we know, as I've mentioned, that where air experiences gravity, so it experiences gravity downward. So basically gravity pulls the air downward, and the pressure gradient or the pressure gradient pushes the air upward. So if you see, gravity is downward, pressure is upward, so you can say that it's basically balancing out. So that's why it follows, or you can also say it's like a pressure gravity balanced equation. You can call it that as well. So now in the equation, as I mentioned, so we know that pressure and gravity are balanced. So now for from that we get the equation. So over here, there's one thing, dp by dz. So over here, pressure is changing with respect to height. It's not changing with respect to time, right? So over here, P is pressure, which is whose unit is Pascal. Z is height or the vertical coordinate, whose unit is meter. That is in the LHS, and then the RHS negative sign, because as we know that pressure decreases with height. So like let's say as we know that mountaineers, when they're climbing mountains, and as they reach at some very high, high elevation, they'll pressure pressure decreases, because of which oxygen level decreases. So because of that they face a lot of problems, so because of that they carry oxygen tanks. So that's the idea, that's the basic reason why we are putting the negative sign, because pressure decreases with height. And so that, and then rho. So rho we know is the density of the fluid, whose unit is kg per meter cube, and g is the acceleration due to gravity. And we know that the value of acceleration due to gravity is 9.81 meter per second square, right? So that's the basic idea of hydrostatic balance equation. And so where is it used? So, and how is it used? For what it is used? So it's used for converting pressure level data to altitude, and it is critical for all vertical grid structure. Now, again, this thing will be explained by Aradhya in a few minutes, or in the further slides. So don't worry about it. And so this equation, hydrostatic balance equation, in conclusion, we can say that it basically explains why atmosphere is stable, why it stays stable. Because as we can see that, pressure and gravity, they're just balancing out, because of which it's just stable. The air is just stable, right? So this is a main ideology of hydrostatic balance equation. Now let's go. Yeah. So next slide, please. So now the five equations that I explained to you right now, which is conservation laws, in which there's conservation of momentum, conservation of mass, conservation of energy, and conservation of momentum, as I told, as I gave you the equation, that we use the Newton's second law of motion, right, which is force is equal to mass into acceleration. And then conservation of mass, in which I told that mass can neither be created or destroyed. It can just change into forms, right? And then I explained conservation of energy, where we use the first law of thermodynamics, in which it is defined as energy can neither be created nor destroyed. It can change into different forms. So that's what conservation means, right? That change in conservation of mass, change in mass is zero. In conservation of energy, change in conservation of energy, change in energy is zero, right? So that was the main idea of all the conservation of laws. And and I'm pretty sure you guys have learned it before as well. So now, and then I explained ideal gas law as well, which is a very basic and a very important law in physical chemistry, which you have learned before, that PV is equal to nRT, and we link it with pressure, temperature, and density. So how we get, and then we multiply and divide with molar mass. We use the density formula, which is mass by volume. We get the equation in terms of density, which is P is equal to rho RT, right? So that was the idea of ideal gas law. And then hydrostatic balance equation, which I explained a few minutes ago, that you can also call it pressure gravity balance equation. How? Because when air experiences pressure in upwards direction, and it experiences gravity in the downward direction, because of which they're just balancing out, right? And then I explained the formula, all the terms that, in hydrostatic balance equation, we use dp by dz, which is change in pressure with respect to height at a fixed time, right? In other equations, we did with respect to time, but at fixed position. But in hydrostatic, only in hydrostatic balance equation, the time was fixed, but the position or the vertical coordinates wasn't, right? So this was the so together they just form a closed system that can be solved numerically. So that was the whole idea of all the five equations. So as the subtopic says, the five equations that rule the sky, right? So now this is the last equation which I'll be explaining to you guys right now. That is the Navier-Stokes equation. So now, as from the title, Navier-Stokes equation, the word Stokes, I mean, what I remembered that when I heard the word Stokes, that we are in 11th or 12th, we learned something called Stokes equations, right? Stokes law, that which was I'm not sure. I guess it was force is equal to 6 pi r eta vt something, right? Where we were supposed to find the force. Eta was the viscosity, and vt was the terminal velocity of the fluid. So the Navier-Stokes equation. So in Navier-Stokes equation, again we come back to Newton. So in this we use the Newtonian laws of fluid dynamics. So in this, as I'll just tell the definition, which is the Navier-Stokes equation, foundational in the laws of fluid dynamics, describes how velocity field of fluid substances behaves under various forces. So it's basically what we learned before, that force is equal to the which we learned about the Stokes law, which was force is equal to 6 pi r eta vt. So the formula given below, it's basically the complex formula or the more advanced formula of what we learned before. So over here, I'll just tell that I'll just explain the terms. That over here, rho again it represents fluid density, right? As we know, and then dou into dou in the bracket dou u by dou t, which is change in velocity with respect to time at some fixed position again, plus u, which is the velocity field vector, into the divergence, the del operator, as we know. So divergence of u, we use divergence operator here again. U is again the velocity field vector, is equal to minus del p. So now that minus is again the external force that is acting in the opposite direction. So minus del p, del is again the divergence operator, and p is fluid pressure, plus mu, which is a viscosity, dynamic viscosity, del square, u del square of u, again it's a gradient, and u is the velocity field vector, plus f, which is the all the external forces acting. Now, why it matters? So if we did not have Navier-Stokes equation, we cannot model wind at any scale, from gusts to jet streams, right? If Navier-Stokes equation wasn't there, if Newton hadn't found this equation, hadn't explained this equation, we couldn't model wind at any scale. So, right? So again, all the relations between the equations and the weather forecast and the weather forecasting will be explained by Aradhya in the further slides. So yeah, thank you, and Aradhya, you can take over.
Okay, thank you, Manat. My name is Aradha Jain, and I will be explaining so we have all so far we have understood that yeah, weather prediction happens and it's uncertain, and there are some equations in the atmosphere. But how do we correlate all this? So as we move on, we see the application of mathematics in all of this. Um, since the atmosphere is very chaotic and you know there's also some structures which makes us realize that yeah, it's not even the initial conditions make a huge error, but each structure is each chaotic structure has some mathematics behind it, which we will understand from the methods of weather prediction. So in the current days we use these methods by move on to the next slide, please. Yeah, so sorry about that. These are the major uh, weather prediction methods which we have in the current days. So the first one is numerical weather prediction, which we will call NWP for now. And then we have statistical methods. Then we have ensemble forecasting and AI machine learning. So these are the four major methods which we will move on. The first we are going to discuss about is statistical methods. So please next to the next slide. Yeah. So what this how this method actually works is that it's pretty simple. It does not use any physics laws or any mathematical complex equations which we discussed earlier, but it completely depends on whatever the data which we had historically, like temperature, rainfall, and then it just plots everything on a graph. So by that we can understand the trend of all the data we have, right? Now in that graph, how do we correlate between two datas? So we create a coefficient for the correlation, and this coefficient ranges from -1 to +1. So there are the three coefficients which we can see. There is +1, which means that if two datas have a +1 coefficient, so it means that they both are strongly correlated, and uh, how much increase occurs in one data is same as the increase in the other data, and same goes for decrease. However much the first data decreases, the same way the other data will decrease. But what do we correlate? Past data and current data? No, we actually correlate the two datas which we have plotted. So, as I mentioned earlier, time series data, temperature, rainfall. So, let's say your data is temperature and rainfall, or let's say your data is rainfall and humidity. Okay, for now, let's keep those as the two datas. Now, the correlation between the rainfall and humidity seems like something which could come in the +1, right? Because they are sort of related. How much the humidity increases, same way the rainfall increases. Now let's say the correlation is 0. So it means that there is absolutely zero correlation or no correlation between the two datas. So same goes for -1, similarly as +1, but completely opposite. So -1 means like one data is how much increases how much it increases in one data, the same way it decreases in the other, and vice versa. So let's move on to regression. What is regression? So regression is the equation we use. We are welcome. Is the equation we use. So let's say we create an equation between rainfall and humidity, which we took earlier. And for example, okay, it's not this simple as it shows. That is, y is equals to a plus bx, and where a and b are just arbitrary constants. But it could be any equation, okay? But for now, let's for easy understanding, let's take y is equals to a plus bx. So this way we can plot it on graph, and we can see how it increases, like in in y-axis rainfall is increasing, and x-axis same way humidity is increasing. So we can see the curve, and we can know, okay, this way they both are related. And then what does this actually gives us? So this way we can find the probability of how exactly a weather event is going to happen. So it calculates the likelihood of that weather event, right? And this also helps us in error calculations. So the predicted data and the actual data are then compared, and then this is then refined to build a better model. Now, although we have been using the past data, so the error calculation is not that accurate, which we'll be talking about later, like what are the disadvantages and advantages. So let's move on to the next slide. Um, we see the advantages of the statistical method is that it's very simple and fast, right? We are not using any physics laws, we are not using any complex partial differential equations. It's very simple and very fast. So it's very easy to implement, and it's excellent for short term forecasts. So I'm not going to say that every time there is the weather is like, yesterday how it was, it would be same and would be alike how it would be today. No, that's not something we can say for every time, but it is mostly gonna happen like that, right? So it is good for short term forecasts, and uh, yeah, that's one of those advantages. And also very important advantage is that it requires minimal computational power. Again, we are not doing any complex equations, so it won't really require any computational power, will it? And it is easy to interpret, and we can explain it very easily. How accurate? Wait, 1 second. How accurate is it for short-term forecast? Do meteorological departments in India still use this method? Well, no. I will be discussing about that later on. That which method we use, and what method is something we would like to use. So yeah, just buckle up. I will tell about everything, right? Yeah. So um the yeah the another method which is there, which is better than this method, is numerical weather prediction. So this method is something which is really important to understand all the kinds of methods which we are going to discuss later on, because this method is something we use in every other method. Okay, so please try to stay with me. How this method works. So we instead of like the statistical method where we take the past patterns, and we do not using any equations, we are actually implying the equations which we studied about earlier. I hope you guys paid attention to that. And All the mathematical equations which we discussed, it implies all of them, and it takes data from different satellites and weather stations which are there for particular interval of time. Let's say for every 6 hours. Okay, so it will take all the data stored from different area stations in that particular time interval, and then for different intervals we assimilate all those datas together. So we blend those observations which we got from each time interval, and then we make it uh, our actual data, which we like actual assimilated data of now, like of right now, which we are going to use. And so how do we start all this, like where do we begin? So first, let's look at the image. In that image, you have seen you will be able to see the grids which are there. So what do these grids do? We map all the datas which we have gathered before, and then we plot it all in these 3D grids. So let's say in we take the map of India, and then we make a grid like this, longitudinal and latitudinal, and then we for each grid we do a different kind of nwp uh, for each grid. Now let's say all those datas are then plotted on the 3D grid. So in each grid there will be different data too, because we have just integrated the data. So yeah, it is pretty time consuming. I will get on to that. So uh, this helps us integrate all the data so that we can work on it individually, and small by small. So those small datas which we have been working on will give us different outcomes, right? Because it is not possible to have the same datas in one grid and others same datas in completely different grid, right? So it will give us different outcomes, and from those outcomes we will make one final outcome. We will discuss on how that works. Let's move on to the next slide. um, so this is basically how entire method works. So first, as we said earlier, there are some partial differential equations which we use for each grade, and from those equations, which previously Manat explained that they describe the motion of air, heat transfer, and pressure changes. We use them in each grade so that we can understand the weather in that particular grade, right? Now, when we use this grid, we cannot exactly predict the solution of these equations, right? So we just approximate it for a while, okay? Now that also tells us that this is not going to be accurate, but trust me, it's not possible to give exact solution because grid has some limitations which we will talk about later on. And now, each grade is solved step by step in those equations over time. So we can actually see the weather grow technically. See, in the previous one, in the statistical method, how we saw the the method, we used the data from previous time, and we applied it today. Here we are actually seeing the evolution, we are actually seeing it grow. So instead of taking its past, we are creating it, or sort of just seeing the evolution of how this weather is going to change grade by grade, like a simulation. Yes. So the future values actually depend on the previous values, but this is yeah, this is how it works. But then also it comes with a small problem, or if not a big problem, that is a small errors occurs. So in those grids, if as I mentioned earlier, we have to keep precise initial conditions in each grid. So if we don't, which we cannot, obviously we're still humans, right? So if we create even a little slightly little small error in each grade, uh, those grade will come along, and it will actually give us the end result will be like completely different than expected. uh, so this explains the fundamental uncertainty of the entire weather forecasting, and that's why it's so hard to predict. As we move on, we will see the advantages and limitations. But first, no, previous slide, please. Yeah. So first, I will actually give the scale of how this method actually is. Uh, so we have like, let's say the Earth is our map, right? So we create like 9 million plus 3D grid cells. That's a lot of grid cells, right? And in each grid cells, we have different kinds of variables, more than six. So, and each step, like each run we do in those cells, is done in thousands plus times steps. So that just tells us that there has been doing billions of calculations per forecast. That is a lot, right? So let's look at the advantages of this method now. Um, uh, Next slide, please. Yeah. So this method is of course more accurate than the statistical method, which you might have already guessed, because statistical method depends on the past, right? But here we are actually calculating everything using real physics laws, and this can predict complex systems like cyclones. So let's see. Let's imagine the grid system which we saw earlier, and let's say there's a cyclone in some part of India. So if we look at the grids where the cyclone is not there, right, which is common and has clear weather, you can see that it does not really have a lot of confusion. It has one, all the outcomes which come in that grid gives us particular answer. So, but in the area where the cyclone is about to happen, on the edges, you will see a slight change in the you will see the slight changes in the grids equation, and you will see like, okay, something is happening. And then the more you move to the center of the cyclone which is going to happen, you will realize, okay, yeah, there is something, some cyclone or storm going on in this area. So it's really helpful to predict this complex systems. And uh, of course, it uses real physical laws, so it's not just patterns. We are actually finding the results. And the limitations on this method is that it requires enormous computational power. So as someone mentioned earlier, that is a lot of time consuming, and it requires a lot of calculation. So this will obviously require a lot of computational power, uh, which is hard to get. So those are the limits, and it is highly sensitive to initial condition errors. So as I talked about earlier, even a small change in each grade can result in completely different answer. So that's a huge disadvantage of this method, and that we will solve later on. So buckle up, okay? And then there is one grid resolution limits spatial accuracy. What this means is that in each grid, if there is a some equation which is smaller than what the grid can give us, so let's say there are some six variables, and we found out that there is more problems, more constraints to this particular grid, we cannot have that, right? So this gives us some limit to the accuracy because we cannot take some other errors, right? So yeah, this cannot resolve the subgrid scale phenomena. So let's move on to the method, which actually is my personal favorite, and it's called ensemble forecasting. Now, this method is actually a game changer, because let us see how this is a game changer. The first thing it does is it varies the initial data. So previously, when in numerical weather prediction method, where we create a precise initial condition, and small errors were giving us different results, right? Here we for the same grid create another simulation for the same grid, but we have different initial conditions, slightly different, and we create that quite a few times, so that we have different number of conditions, and so that we can get one particular outcome. So as we move on to another step, it says run NWP model. So we are running NWP models every single time. So we are not just doing it once, which we did in previous method, but we are doing it more and more with different initial conditions. Now, how do we get a particular output from this? So what we do is we compare the outputs from each kind of simulation we did. So we are doing different kinds of NWP methods, right? So those outcomes will we will compare those outcomes, and uh, let's see, it shows us that in the total, right, it shows us like 70% of the outcomes are saying that it will rain. So it will give us a guarantee like, yeah, it most likely will rain. So this will help us reduce the errors, because it has more outcomes and more initial conditions. So, and we are then comparing all of them, so that we can get one particular solution, which we will discuss how we compare. But we will be able to analyze how one outcome is certain. How do we do that? We actually have a spread. So what is a spread? When different outcomes give different kind of, like, let's say someone is saying rainfall, someone is saying snowfall, someone is saying something else, right? So the spread means that how much we are getting those particular weather event in each kind of equations, uh, the more spread spread out it is. And if we are getting it less, like we are not getting much of it, but we are getting different kind of weather events, uh, then the more spread of different kinds of outcomes it is. So that makes it uncertain, like what could be the possible outcome. But when it's like majorly that one particular event, which we said, like, 70% rainfall, so the spread of that rainfall is actually low. So it will give us high confidence, like, yeah, rainfall is most going to occur. Now let's look at the mathematics behind this method. So um, what happens is that, as we said earlier, we have small controlled changes. So instead of having one initial condition, we actually change the initial conditions. So it actually represents the real world measurement error, right? So how do we get one particular solution from this? We mean all the predictions. Let's say we did n predictions. So we mean those n predictions, and the mean will give us the central most likely forecast. Now, of course, it won't always be available from mean, because there could be different kinds of weather events happening. So how do we know how many weather events are happening or not? So that is how we found out from standard deviation. So when we plot all this on a graph, we can actually we can actually find out the standard deviation of each weather events, and this measures the disagreement between the members. So the members is actually uh, called the ensemble members, and ensemble member is basically one ensemble member is where we are doing the particular NWP's model. So like different kinds of NWP models means different kinds of ensemble members. Okay, so as we discussed earlier, if the standard deviation is small, there's a high confidence of that particular event that it's going to happen, and vice versa for the large standard deviation. So what does this actually give us? So this gives us the probability of that particular event. The formula for the probability of that particular event, which we might all already have guessed, is that the members predicting the event, the particular event, upon total members. So all the members, no, all like the particular members of that the event. Let's say we want to find the probability of rainfall. So the members which are saying, yeah, rainfall will happen upon the total members, like any rainfall, snowfall, everything in that particular data. This is what gives us the probability of that particular event. So this converts the like where we used to run each simulation. This gives us the likelihood of the event. So instead of solving, we are actually getting the likelihood, right? Now, how do we distribute all this? So we plot all the outcomes, and then we visualize the uh, we will be able to visualize all the possible futures which we might have while plotting all these outcomes, right? So this actually reduces the error. How does it reduce the error? When we average the different kinds of prediction which we have, it actually cancels out the random errors. So let's say when we average out that rainfall is there, and we see that rainfall is happening a lot of times. So when we average out and then we find out that rainfall is in this particular way, then the random errors which were happening in that part will get removed, because we got the average. uh, so yeah, that improves the accuracy of the final forecast we have. Now let's move on to the how we read all this forecasting. Let's first talk about the distribution which we talked about earlier. Um, as I said earlier, when many members cluster around one value, high confidence, so high probability of that event. So let's look at the spread concept. The 90% and the percentages below, like 75, 60, 35, 45, 30, they all signify the probability of that particular event happening. So in that 90% one, all the spread, it has the least spread, so it is most likely going to happen, and thus it has the highest confidence and highest probability of happening, which is 90%. And then same oppositely goes for the 30% one. Now I have my two personal favorite representation which I would like to share. Let's move on to the next slide. So there are two ones which I really like, is spaghetti plots and probability maps. So in spaghetti plots, we can see in the image that in that particular, let's say there's a straight line, right? In that straight line, we can say that it's quite predictable. Okay, this is going to happen like this. This is basically, these lines you see are what the ensemble members create together. So when we plot this on the graph, we see this particular kind of design from the ensemble members of a particular event. This is not for all, but a particular event. So uh, uh, we can see the change in the lines, which makes us realize how unpredictable it could get. And as we discussed earlier in the Lorentz attractor, we can see that it becomes very fan shaped, and it becomes very curved and circle type, very circular loop type, and that is very chaotic, because we won't be able to tell what is going to happen next until we do a lot of calculation, and then only we could predict that. And the next is the probability maps. Now this helps us realize the what uh, how much more likely it's going to happen in that particular area. So let's look at the image. There are some legends given down below. Snow is white signifies snow. Uh, Brown signifies heavy rain, and the blue signifies mixed precipitation. So what this means is that in the snow part, in the white region, it's more the ensemble members of snow is most, so the where we saw the less spread and more probability. So here the spread of snow would be less, which means it's giving high confidence that it's most likely going to snow. It's not certain that it's going to snow, but most likely the probability of it happening is highest among all the other weather events which could occur. So, and same goes for rainfall, but in the blue one, which is mixed precipitation, it actually means that there is no single precipitation which we found to be like the most highest one and has the least spread, but each of them have equal or almost same spread. So we couldn't tell the difference. So this is what a mixed precipitation result would occur. Now let's move on to the next slide. Here we discuss the advantages and limitations of ensembles. Now, the advantages of this method is that it provides probability-based forecasts. Now, since this method is not like NWP, like it uses NWP, but it's not exactly like NWP, and especially not a statistical method, right? So this actually makes it probability based. So we are not determining, okay, this event is going to happen, but we are actually determining, okay, this is most likely to happen, right? So this gives us more idea of what could occur and what could not. And it explicitly accounts for atmospheric uncertainty. As I said, we are not determining the which weather would happen, but we are determining the likelihood. So it would help us understand the uncertainty. Now it's more reliable for risk assessment and planning. Now in situations of emergency like natural disaster, where we have to evacuate people from particular region, we uh, do this method on that region. Like the map is that region where this natural disaster is occurring, and hence we using this method to, like, okay, the probability of happening here in this region is less, so we could evacuate the people here easily. But here it's more, so we have to hurry here. So this helps us in planning, okay, in evacuation. And that's a very important thing and a very major advantage of this method. Now it identifies multiple possible weather scenarios. Yeah, same probability base. Now the limitations on this method is it's computationally very expensive to run. Again, we are doing a lot of calculation, and not just once but many times. So and we are all plotting that to a 3D grid. So this gives us a quite basic idea that, yeah, it's going to be very expensive, right? So yeah, the interpretation can be complex for end users. So yeah, the result we get it it's not direct result, right? It's probability based, so we still have to think about it, and it's not straightforward. So it could be quite complex for some normal users. So it's not a really nice idea to use this method by them. Now, quality still depends on underlying model. So yeah, the better the model we have, the better the better result we would be able to get, as it requires a lot of equations. So yeah, that was ensemble method. Now let's move on to the next slide. This is the method which we use in the modern world, that is AI and ML method, or artificial intelligence and machine learning method. So what this method does is that it uses algorithms and data-driven models to learn patterns and predict weather. So we are doing the same thing which we did in previous ones, but now we're not just collecting the data, but we are actually training on that data. So whatever model we create from those data, we train them to create a better data, and then billions of data uh, is in front of us, right? We have a lot of data available rather than some. So why do we train? Like, how do we train? So first what we do is that we learn the patterns. So the model learns the correlation between the inputs and the outputs. What are the inputs? Let's say humidity and pressure, right? You just input them. So what could possibly happen? There could be change in the probability of rainfall. There could be change in the rise of temperature. So this helps us in this is what we train the model to understand better. Now, not only this, not just training and everything, but we do it multiple times. So we optimize this particular data we have by doing multiple training iterations. Now, with gradient descent. Gradient descent is something I will explain later on, and it's very important. This it is what makes this method stand out from others. And um, so this kind of iteration and optimization is actually what helps us reduce the error which we have. Now this a trained model is applied to current real-time data. So the trained model which we have, we use it. We use all the knowledge it gathered from the past, and all the multiple iterations which we did, and then we use it on current data which we have. So we get to know, okay, when this happened previously in the past, let's say humidity or pressure, something happened, then we got rainfall. So this might also give rainfall. We will understand this better in the next slide. uh, Please move to the next slide. Yeah. So how does mathematics actually power AI/ML? Uh, so the data representation of this method is completely different from the previous methods. We use the language of linear algebra. That is, what we do is that when we collect the data, we represent all of the data in numerical vectors and matrices. This helps us reduce the complexity of the data which we had, all the equations which we had, and all the nonlinear equations which we had. It helps us reduce all of them, and it makes it easier to understand. Now, uh, again, we you find out the relationship between the input and output, which I said earlier. But how do we do that? So we create a function with the parameters of the output. So the y here you see is the output, and the x here you see is the input. So we create a function with the help of the x and the which is our input, and the the theta, which is the parameters which we got from the inputs, and then we create a function based on that, which gives us the output. This relates the input and output. Now, how does this help us? So when we see that, okay, this particular parameter of input is given, Okay, so this means that in the previous function which we had created, it gives us that particular output, which is predicted rainfall. So let's say for example, we got parameters like humidity and pressure. Again, the same examples, right? So as we saw earlier, when humidity and pressure come together, in the previous past, most likely there has been rainfall. So the output from this function we get is the predicted rainfall. Now comes a very important point, is that we create a loss function. How do we calculate the error which comes from this? So we create a loss function by comparing the predicted and actual measures. So let's say there's a function where the no it doesn't necessarily have to be this easy, but for now let's say there's a loss function where the difference between which is the difference between the actual measure values and the predicted values. Okay, so which we can see is y cap minus y. So y cap is the actual measure and y is the predicted measure. So this is the loss function we have, and this tells us how wrong the model is. Now comes the most important part of this method, and this is what makes this method stand out from the others. This is gradient descent. Now, what exactly is this? So the L here you see down is the loss functions which we created earlier on, and the theta here is the parameters which we had found earlier. So what we do is that we derivate the loss functions which we had with respect to the parameters which are there. Okay, so let's say for example, okay, you are in top of a mountain and it's really dark. Okay, and you have to get back to your village which is in the valley. Now you don't know, you cannot see anywhere because of course it's dark, so you are not able to like predict where your village might be down the hill. So whatever the first down slope you see, you try to go there, so because you know your valley is down, so you whatever value is whatever downhill you down slope you see, you will try to take that. That is exactly how this works, but imagine the gradient as the downhill and the parameters the error which we have as the top of the hill. So you want to go down there which is less error, which has less error and more accuracy, and you're on the top which has the most error you have gotten uh, from the accurate result, right? So what we do is that we change the parameter using a formula for now, which is theta minus alpha into gradient of L. So alpha here is the um, rate of error which occurs, and a gradient is the change in the steps you have in the law like okay, sorry, the gradient of L is the change in the error which occurs after your each step you take, and theta is the parameter. So this helps the model improve the data which is there by reducing the error. So this is how the AI/ML works, and let's move ahead. Um, well, let's discuss the advantages and limitations of this method. Now, this method is extremely fast, okay, because it does a lot of calculations, and it learns from its own, it trains the models and it learns from its own mistakes, as we discussed in the gradient descent. So this is quite fast once trained, but and also it handles massive and multi-dimensional data sets easily. Since we created all in matrices and vectors, it helps us reducing all those complex multi-dimensional um, like equations which we had earlier on. So it helps us break it down and find the results pretty easily. It also improves automatically with more training data, as I said earlier. Due to gradient descent, it helps itself improve itself, and then gives us more accurate result. Now, there are a lot of limitations on this method. Again, the first and the most obvious one is that it requires enormous amount of training data. Now, of course, if we are making a model which requires different kind of equations and has very a lot of complex equations which we have calculated into a simpler one, yet there is a lot of them, then it requires an enormous amount of training data, because you still need to train it all, uh, it from the previous data, right? uh, it lacks physical interpretability, as it does not really tell us a lot about uh, what could happen. And then, right, can fail badly on unseen weather patterns. Now, this is important because, let's say an AI learns about a particular weather event from the past predictions, right? So that particular event must have happened sometime in that particular past time, past patterns, so that it could know, okay, this happens, so we have to do this. So it trains its model in that way. But what if it is the first time that the weather event occurred? So uh, that just completely ruins, or maybe just stops the method to do anything, because it can't train itself for something which it has never seen before, right? So this is a very major disadvantage and limitation on this method. And yeah, so there are some other methods other than these, uh, but they are pretty useless. Like, let's say the persistent method, it assumes weather remains the same as current conditions. No, it is exactly how it sounds. It's very short. It is best for very short forecast. Like, in today itself, we will talk about like, okay, at 3 p.m. the weather looks like this, so at 6 or 4 p.m. it must also look like this. Now, that is such a huge assumption, because of course it's not going to be the same. So that's why it's useless beyond a few hours, because it will obviously differ a lot from the previous ones. Then there is climatology method. This uses long-term average conditions for a location and season. Now, this is good for planning. Like, if you're a tourist and you want to know, okay, I want to what is the best month for what is the best month for tourism in Mumbai. So it will tell, like, yeah, Mumbai gets heavy rainfall in July, and but it has a very pleasant um season in March, although it doesn't, but let's say it says that. So it is best for seasonal and long range planning, but it completely ignores the current atmospheric state. Now, that's something which we can tell, because what if in July only there is some days, few days where it heavily rain, but then like in the other few days in July itself, it's like clear sky. So what do you do? So that's how useless this method is. There are a few more, like, please move on to the next slide. There are a few more, like analog method. Now, this compares the current conditions with historical analogs. Now, what this the method does is that uh, it finds past situations that most like closely match today. Like, it might have found, like, okay, in July 2024 this might have happened. So, okay, not exactly that, okay, my bad. But let's say previous month this might have happened, or previous week this might have happened. So most probably, if last Wednesday the weather was like this, then this Wednesday also the weather should be like this. Now, that's something you cannot trust, right? So it's only valid for medium range forecast, as only 3 to 10 days. And it's really rare to find exact historical matches like this, because of course the weather changes every day, uh, even every hour. So it doesn't really it's not really possible to have the same match. But yeah, that's how that method is used. Now there is nowcasting method. Now this method predicts weather for the next few hours using real-time radar and satellite data which we get. So it's actually really nice for thunderstorm and heavy rain alerts. Like let's imagine there is some thunderstorm like going to happen in the next 3 or 2 hours. So for the you might have seen on Google like red alert in Mumbai or red alert in Vellore. So that's how like it tells us like, okay, in few hours this is going to happen, so thunderstorm. And it gives us quite a good alert, but only used for short time intervals. Of course it wouldn't really have good knowledge for the next few hours. So these are the methods. And as we move on to the next slide, um, um, yeah, I can please move on to the next slide. Yeah. Uh, as we move on to the next slide, let's get a brief on what the methods I talked about, especially the measure methods. The first one was statistical method, which we talked about. Now, the compute cost of this is pretty low because it only uses the past patterns, so it doesn't really have any equations or physics laws which are implied. So the forecast range will also be short term. Like it is only possible if like few days ago or few 1 or 2 days ago the weather was like this, so most likely it's going to be like that today. So that doesn't really give a good like confidence in the weather, so its accuracy is very low. But yeah, that's how this method is. And then there is in numerical prediction, which has of course a very high computer cost. And it can give us a good range of forecast about around 7 days, and the accuracy is pretty much high. So it is pretty good, but also it requires a lot of computational costs. Now there is ensemble method, which requires extreme cost. And the range is again around 14 days, and the accuracy is pretty good. It's more than the previous two, and it's actually really nice and can be trusted on for a good time, like for a good amount of time. Now the AIML one is actually really high computation cost, and it's really good for like short and medium time only, but the accuracy is very very high. So you will get almost uh, near perfect, of course not perfect, but near perfect accuracy on the results using this method. And this is why we use this method in the modern days. And let me just conclude on what I just gave, what I just talked about. So at first we learned that the weather prediction is very hard and the atmospheric is very chaotic. So this could be very problematic. So we solved them using some four methods, which in the first one, as we talked about earlier. So this method tells us that each method gives us different truth about the future. So each method has different outcomes and have different advantages. So what does that tell us? This tells us that there is no single weather prediction method, but there is actually different but we can actually use all these methods for the best result we could get in particular circumstance. Like as we saw earlier, for a very short interval of time, the numerical weather prediction is actually really nice because it has less computational cost than the others. But it also tells us a lot about uh, the weather and has a good amount of accuracy in that short interval of time. So this tells us that we cannot have one particular predicting method, but we can have good results using all these, right? now what can we do to improve this in the future? So the one we can trust the most is the AI ML method, because it has very high accuracy. So if we could advance more in the the computing power, and we can have more uh, less expensive in those expenses in those and more ability to solve the different kinds of uh, equations, then it will actually gives us better and very more far more precise results. But one thing will be certain, that is chaos will always set a limit, and that is something I think we have all understood till the by the end of this lecture. So thank you everyone, and I hope you guys enjoyed this lecture about mathematics behind weather prediction. And one last thing, that we are not going to leave you guys without any quiz, right? So, Manat.
Okay, so now before we wrap up, now we have a quick 15 question quiz for you guys. So one of my teammates will be sending the link in the group, in the chat box. So it's based entirely on what we just covered. It's based entirely on our presentation, from equations governing the atmosphere to the chaos theory and other prediction methods. So it's not tricky. They're simple questions. It's just a fun way to test how much you picked up, how much you followed us. So, and remember, there's no negative marking. And so try to attempt each and every question, and each question carries 1 point. And you guys can just copy the link and solve the quiz whenever you guys are free or whenever you have free time. Thank you very much. So yeah, you can just copy the link and solve it whenever you want, and you can leave the meeting. Thank you
I hope you
for
guys enjoyed the
joining.
meeting.
Thank you very much. You guys can just leave the meet if you want to. I mean, we are done with the presentation, and whenever you guys have any free time, you can just solve the quiz. You can copy the link from the chat box. Aditya and David will ask our board member and get back to you.
Guys, the form for the attendance is in the chat. You can fill it and leave. Thank you.